So now we're going to talk about mechanical energy. Let's say when you have a system, and mechanical energy basically is the sum of kinetic energy and the potential energy. So we use capital E to indicate that's mechanical energy. It consists of two terms. So you have K, which is 1/2 mv squared, and plus U. And we're not going to specify what kind of expression for that because it really depends on the system. If you're dealing with the spring, then you have the US. If you are dealing with the gravitational force, then you have the UG. Okay, so this is the energy of the system when it consists of kinetic energy and consists of the potential energy. And we know that within the system. So let's say this is a system. Okay, so we draw that this is the boundary of the system. So it involves two kinds of energy. One is kinetic energy, and one is a potential energy. So how do we change the kinetic energy or the potential energy? If we want to change one of the quantity, how would you do that? Like that. So how do we bring the object up? Going up the ramp. So you have to apply a force, right? Yeah. Okay. So in other words, if you want to change this quantity, how would you change that? You have to apply a force. And the force is, it's going to do work. And remember, what is the definition of work? Work is energy transferred to or from the system. Now, within the system, work is done by the force to transfer energy from one form of energy to another. So you have to have a work. You have to have a force. That force is applied to change the either configuration or change the speed of the object, so that kinetic energy would change and also the potential energy would change, right? So work has to be involved. A force has to apply in order to accomplish that. So in other words, you will have, if you remember, the change in kinetic energy is equal to the work done by the force. This is work kinetic energy. And we also mentioned that the change in potential energy is equal to negative work done by the force. So when you add this two together, what do we have? On the right-hand side, you get 0. When you have a 0 on the right-hand side, it doesn't mean that there's no work. There's work, but then the net work is 0. So in other words, during the intermediate state, when energy is transferred from one form to another, there is a work that's doing the work, but then the net work, when you add them together, the net work is actually 0. Okay. On the left-hand side, what do we have here? We have delta K plus delta U, right? And what is the definition of delta K? We know that it's W, but in terms of the definition of delta, what is delta? Final kinetic energy minus initial kinetic energy, right? So that's your delta K. Now, what about your delta U? Your delta U is the final potential energy. Right now, we haven't specified what kind of a what kind of a potential energy. Let's just say it's a potential energy. So UF minus UI, right? That's just definition. That change. The change is, of course, is the final value minus initial value, and the whole thing is equals to 0. So what we're going to do is that we're going to group this two together. So what we have here is that the final kinetic energy plus the final potential energy is equal to, and then we're going to move this two negative quantity to the right-hand side of the equation so that it becomes positive. So we have the Ki plus Ui. So let's look at this. What is that? The final kinetic energy plus the final potential energy, that's just basically the final mechanical energy, right, of the system. So this gives you this. And what about this? Ki plus Ui, that's just initial mechanical energy of the system, right? So what does that mean? When you have initial energy and the final energy, they are equal to each other. Zero network, that's right, that's zero network, and energy is conserved because This is the energy you started with. After going through different processes, whatever process that might be, there's a force, there's a work, but then after all is done, you still find that the final energy is still stays the same as the initial value. So which means that energy is conserved. Okay? So that's an important concept. Energy is conserved. When you have an isolated system, and the force that does work basically transfer energy from one form to the other. Okay? It doesn't mean that there's no force. There is a force, and the force does work, but that work is transferred from one form to another. So you can lower the energy or increase the one of the energy. Okay? So that's that. So energy, of course, is a very important concept in physics. In physics, everything is about is about energy. And within an isolated system, which most of the time, this is what we are dealing with, energy is conserved. So whenever you have a system, you start with, let's say, 5 joules. After you go through the valley, after you go through the, all that, processes, you'll find that the final value still stays the same. That's because energy is conserved. And provided that if you include all kinds of energy within that system. Right now, we're only dealing with the mechanical energy that only involves 2 forms of energy, like kinetic energy and potential energy. There might be other energy as well, which you're going to learn, the energy that involve with the frictional force. Okay? So, and let's see. So, we, let's say, another thing that's for your information. We know that work and force that relate to each other because you have to apply a force. You have to apply a force in order to do work. So work is basically equal to, if you remember, that's F dot D. Okay. Now that's say if we don't have this work, the total work. That's say we have infinitesimal amount of work, the small differential work. Then you have your dW that's equal to. Do you remember what that is? You have your D, and then you have this, F dx, right? So this is the small amount work done by that force when the displacement is so small. So this is differential form of work. So dW is equal to F dx, okay? And so in that case, your force. How do we find force? If you know work, and then over dx. So this is I don't know if you learned that in calculus. When you have dw dx, that basically is a gradient. Are you familiar with that term, gradient? Okay, so your F is just dw over dx. What I'm going to get at is that if we replace our work by this, so in that case, your du, instead of a w, now it's dw. So your delta now becomes du. So your du is equal to negative dw. And then we're going to replace dw with negative du. So the force is equal to negative du over dx. So again, that's say if you know the expression of your of the energy, then if you take this differential form, you can actually find out the expression for force. That, of course, is just for your information if you not quite grasp what is going on here. Okay? All right? All right, so we mentioned that within a system, if you want to change kinetic energy or potential energy, a force has to apply to be done within that system to change one energy from the other. What about when you have a system and you have an external force, and that external force is going to do work onto that system? What's going to happen to the energy of the system? So that's it. Now we have the system, and we're going to do work. So that's apply a force. So you have the force that external to the system. So you have external force that's that is doing work on this system. So this force can do positive work. So that's it. If the directions of work is this, it means that force does positive work. When that force does positive work, what is the implications of the energy of the system? So that's it. The energy of the system has E. if this force does positive work to this system, would the energy of this system change? This is a little bit different from what the previous picture. When you have within that system, and you have work you have force that does work within that system. Basically, the total energy of the system does not change, right? But then now, this is a system. This system has energy E, and then you have external force that does work on the system. And let's say if that force does positive work, would that energy change? Would the energy of the system change? And in what way? Is it going to be increased or decreased by the applied force? This is like, when you're driving a car, okay, and then within the car, the fuel, the whole car is running, and then it's like taking the gasoline, right? And then, so your car is running on the gasoline, and the gasoline is running low, so you have to go to the gas station to pump the gas. So when you pump the gas, take for example, when you pump the gas to the car, this is external to the car. Your car is a system. So you pump the gas into the car, so the car gets more gasoline. So does the energy of the car increase or decrease due to the, yes? Increases, right? Exactly. So in other words, when you have a system, and when you have an applied force to that system, and that force starts its positive work, it means that the energy of the system increases. And then you might have a force that still in this does work on this system, but then it takes away energy. When it takes away energy, work is negative, and the energy of the system will be lower. So in other words, when you have W that's greater than 0, it means that the energy of the system increases. And when you have when you have force that does negative work, it means that the energy decreases. So it really depends on how you define your system. And as I mentioned, within the car itself is a system, and you pump the gas into the car. That is equivalent to you adding more energy to the system. So the energy of the car increases due to the increase of the gasoline. Okay, so in other words, instead of saying that your work within the system, that's if you remember, your work is used to change the kinetic energy within the system. So work is equal to delta K, or work is equal to negative delta U. Now, when you have the external force, that external force is going to do work, and that work is going to change the mechanical energy of the system. So this is kind of like a broader, when you look at a broader picture. So W, now it's the work done by external force that's equal to delta E, the change in mechanical energy. Okay, so that's basically that. And of course, the mechanical energy involves two things. So this external work can be used to change either the kinetic energy or the gravitational potential or the potential energy. Either one of them or all of them. It really depends on the kind of process involved during the change. Okay. Okay. So, any questions so far? So we've been talking about the forces that are conservative. What about when you have a force that's non-conservative? For example, a friction. Friction takes away energy. So how do we account for the amount of energy that's being taken away by friction? So let's look at a typical example. So let's say when you have a block that's moving along this floor. So let's say this block has mass m, and it's moving initially. We call that V naught. It's rightward. And then after you move some distance, let's say a distance of d, its velocity has been lowered by, and then changed to Vf. Instead of V, let's use just V. So you have V naught, that's initial velocity, and the final velocity, we just use V. And the distance or the displacement is your d. And let's say now we're going to consider friction. So there's a frictional force acting on this object. So this block is moving and it changes its velocity. That's because there's a force acting on this object. So let's say there's a rightward force that's pushing this object. So let's say this is the force. Okay? So this is the pictures that we have here. You have the block and experience the force, the rightward force. So this block initially starting with the initial velocity v naught, and it's going to move a certain distance d. And then when it reaches at that point, the velocity is actually changed to to v. And so during this move, it experienced it experienced the frictional force. What kind of frictional force does it experience? Static or kinetic? Kinetic, right? Because it's moving. If it's moving, which means that this block experiences kinetic friction. And what is the directions of kinetic friction? To the left, because it has to be in the opposite directions of the motion. So it should be, let's say, drawing this. So this is your FK, and for a free body diagram, I'm just going to move it up here. Since this is a vector, you can do that. So you have the frictional force acting on that, and then simultaneously experience gravitational force, that's your mg, and then the normal force. And as you can see from this diagram, the vertical forces, they cancel each other. It doesn't really matter, all right, because it's not moving in the vertical direction. So the vertical forces have to be, cancel each other. Rightward, what is the net force in the rightward direction? You have force that's rightward, you have frictional force that's leftward. What is the net force along the horizontal direction? F minus friction, right? So that's the net force. The net force that the block experiences in the horizontal direction will be the force minus Fk. So this is the net force. Now we're going to apply Newton's law. So net force is equal to, what does net force equal to? Ma, exactly. So you have your Ma, right? And this is how you find the acceleration. And that is just the difference in the net force in the horizontal direction that's equal to ma. So in that case, we're just going to keep that. And then we're going to use the equations of motion. This particle initially has a velocity v naught, moving a distance d, and it reaches a final velocity that's v. And so out of the three equations of motion, which one that relates the velocity, the displacement, and also acceleration? Which equation is that? V squared. V naught squared. 2a delta x. So in this case, that's just d, right? Okay, so final velocity squared is equal to initial velocity squared plus 2a times d. So this is the equations as usual. Right? This is just nothing magic. That's from the chapter 2. And then you have the force. So this give us, this give us the acceleration. If you recall, in chapter 7, when we derived the relationship between work and kinetic energy, we did not include friction. Right? So, and we use this equation, so there's no frictions here, and then the force applied is at an angle. In this case, we apply a rightward force to make it simpler, and then there's a friction involved. So the net force is F minus Fk, and that's equal to Ma. We're going to express our A in terms of these forces. So we have the applied force minus frictional force over the mass of the object, and we're going to replace our A with that expression and see what we get. So you have your V squared, that's V naught squared plus 2 times your acceleration, which is F minus Fk over m, and then times your d. And what we're going to do is we're going to multiply n to every turns divided by 2. On every turn, so what we have here is that we have 1/2 mv squared. That's equal to 1/2 mv naught squared, and then plus your F minus Fk times d. Okay? So what is 1/2 mv squared? That's your final kinetic energy, right? And that's equal to 1 half mv naught squared, which is the initial kinetic energy. So when you move this 10 to the other side, that gives you the change in kinetic energy. So we're going to write it like this. So you have your delta K after you move 1 half mv squared to the left-hand side, and that's equal to F times D. I'm going to multiply out F times D, and then minus Fk times D. What is that? What is this? What is Fd? That's work, right? F times D. This is applied force. D is displacement. So that's the applied force. And that's minus Fk times D. So we're going to actually move this to the other side. This turn to the left-hand side. So what we have here is that the change in kinetic energy, and then plus this frictional force times displacement. And that's your work. Okay? What's on the left-hand side? The left-hand side is basically the mechanical energy of the system. You have that involves the change in kinetic energy, that involves this term, which we're going to call that's associated with the frictional force, and then that's equal to the work done by the applied force, which is W. Okay. So what is this? This is what we call the change in thermal energy, and that involves your Fk, which is kinetic friction, and then times displacement. So you can see that. Now, the amount of work that is done by the applied force, not only it has to support the change, goes into the change of kinetic energy, it also goes into the energy taken away by frictional force, because this energy basically lowers the energy of the system. This is the frictional force, and it's path dependent, because the longer the displacement, the larger this term, which means that leaving this delta K smaller, because most of the energy goes into the thermal energy. Okay, so in that case, and then we know Fk is just mu K, the kinetic frictional coefficient, and then times the normal force, and then times your D. So this expression is another expression for the energy, and that's just the thermal energy dissipated by the frictional force, which is Fk times D. Okay? So you can see that what it means is that this work, now, if there's no friction, then you don't have to consider this term. But then, if there's a friction now, this work goes in to support the delta K and then this term. And then you might wonder, for mechanical energy, there's another energy, right? Where's the another energy? Why didn't I list it? What is another energy? I included kinetic energy because there's a change in velocity, and I included the frictional, the thermal energy because there's a friction. What would be another energy? Potential. Why did I not include potential? Delta Y was 0, exactly, because they are on the same height. So when they are on the same height, you don't even have to consider gravitational potential energy, even though there's a gravity. But because they are at the same height, you have on the right-hand side, that's mgy, on the left-hand side, that's mgy. They're at the same height, so you don't have to consider. So that's why I didn't even include that in the equation. Okay? Right, so any questions so far? So that just gives you an idea. So this is an important concept that energy is transferred from one to another. You can change the kinetic energy in the form of a potential energy and vice versa. And in addition to that, when there's a friction, then there's a thermal energy involved that you also have to consider. But within the system, energy is conserved. Okay, so the work done by the force goes to change the kinetic energy and goes to being dissipated by the thermal energy. But when you consider the whole thing as a system, it is still a confined, isolated system, so energy still has to be conserved. So that's why you have to include this term, so that energy is conserved. The other thing is that the last concept I want to talk about is that we mentioned power in previous chapter, and power, if you remember, is defined as the work done by time. This is instantaneous power, right? Is that right? Delta T. This is average, right? Yes. Huh? This is the work, right? Yeah. Okay. So. All right, okay. So the average power is defined as work done, the rate of change of work that's being by the force. So you have the average, and instantaneous I think is dW dt. In other words, you can take the small amount of work and then over the small amount of time interval. So P is dW dt. So the only thing I want to mention, is that instead of just using work, you have the energy of the system, mechanical energy. So if you want to find the average power of that system, if you know the energy, the mechanical energy, then you can just use this equation, the change in mechanical energy over the time interval where the change took place, and that's your average power. So delta E over delta T. And instantaneous power, so P is actually power. So that will be just dE, differential E over dt. Okay, so you can see that this basically is this. So instead of using the work, the concept of work, now we're just using the energy of the system, the mechanical energy of the system, so that's dE over dt. Okay? All right. So that concludes chapter